So the session's about Gaussian processes for unsupervised learning, but it's also going to relate to an area known as manifold learning, because the way the Gaussian processes are used in this context does closely relate. So what the first part's going to be is a bit of review and a bit of philosophy around manifold learning. As I've said, if you check the link, and let me just share the relevant page. So you go to sort of ML at CL, R250, you'll see that there's notes on there. I'm going to share them on the screen and just go through them a little bit to give you the sense of where we're going to go today. So, and then you also get to see my messed up slides. I'm not going to show you those versions. Is it this one? Yeah. So these are the notes, and they cover broadly everything we're going to talk about. There'll be typos. You can actually, if you want to submit a correction, you can click on these edit things if you see a typo, and that correction will come through to me via GitHub if you edit the relevant page. So what you'll see is that we're going to start actually by talking about linear dimensionality reduction before we go into nonlinear dimensionality reduction. So this whole first part is really sort of background that we'll do in the first hour that will lead us into what later is the ability to do unsupervised learning with Gaussian processes, which I'm just sort of scrolling to now. Okay, so you know, feel free to have a look at the things on the side. Of course, if you get distracted a bit, we'll have the recording, so you can go back and listen to the recording. You know, I know if you're anything like me in lectures over this sort of period of time, the mind wanders, but the nice thing is we'll have the recording here, and you'll be able to go check back at it. Right, so any questions before we start? Okay. So, motivation. So, one of the things that I think really interests me in machine learning is high-dimensional data. And it comes up a lot in machine learning. So something like the USPS dataset, which was an early handwritten digit dataset. It was used in the first convolutional neural network paper, has digits which have 3,648 dimensions. So 64 rows and 56 columns or something. But if we look at this space, then if we were to sample, so I'm interested in like just the size of this space. So you can see this 6 here, it lives in a space that is 3,648 dimensional. Now that means that the number of possible images we could see in this space is 2 to the 3,648. So here's like a couple of samples from that space. Now I'm creating these samples by taking each pixel and independently switching it on with a probability that is equal to the number of on pixels in the original image. And what you can sort of quite straightforwardly show, that's such a big number, 2 to the 3,648, that even if we were to sample these sort of images from now until the end of the universe, you would never see that original 6. So I'm trying to give you a sense of, and you may have this sense already, but I'm trying to remind you your sense of just how big these high dimensional spaces are. That, you know, they're absolutely enormous, and we're interested in a very, very small proportion of them. So when you look at models that say, well, I'm going to model each of these pixels independently, they're problematic. And those models, in some sense, actually, that analysis leads to something called the curse of dimensionality, that in very, very high dimensional spaces, everything's equally far apart, all these sort of things. And all those analyses are assuming that the pixels in here or the features of the high dimensional space are independent. They always start with that. If they're not independent, a lot of the curse of dimensionality isn't true. And in general, of course, for real data, they are not independent. They are the strong dependencies. This is the sort of data, I mean, what does this remind you of actually? It doesn't look like data at all, does it? It looks like noise. So it's not, in some sense, it's an interesting observation, but in a very real sense, it's not like the way we see data. Australians say data, I say data, apparently, data in the real world. Okay, so I want to think of an alternative model for such data. Instead of thinking of it as like there's each of these pixels is being sampled independently, what I want to do is imagine I've got a prototype, which I'm just going to take as the original 6 from the USPS data set, and we can rotate this prototype. So if I push this through an image rotation, you can see that I get a set of 6s that all look reasonably like you might expect a 6 to look. Of course, it's the same prototype that's being rotated. And what I'm going to argue is something like this is a better model for data. Of course, these pixels are no longer independent. There's strong dependencies between these pixels. And that this type of thing is a better model for how we should think of high dimensional data. So what I'm showing you here is the first 2 principal components of a data set where I've taken that 6 we've seen and I've rotated it 360 times. Each of the red crosses in the left-hand picture is, just focus on the left-hand picture for the moment, is one of those rotations, okay? And then what I'm showing you is the first 2 principal components of that data. And what you can see in this very, very high dimensional space, when we look at the first 2 principal components, we see a circle, which I think in retrospect perhaps isn't surprising, but when I first did this, I first had this idea, oh, I could illustrate this idea by doing rotation. I actually didn't expect to see such a clean circle. It makes sense in retrospect, right? But I didn't expect it to be so clean. I mean, there is some little bits of noise, and I think that the noise is coming. So look here, this cross, for example, is slightly off the axis. I think the noise is coming from the bilinear interpolation algorithm that's being applied when you do image rotation, because of course, you're rotating pixels. So you can't do a pure rotation. So you do a rotation and sort of interpolate how you're going to put the pixel back in. So I think that's where the noise comes from. But it's a very pure circle. The original 6 is somewhere around here. And actually, I've shown some samples of what the 6s look like as we rotate. Yeah, so this is the original 6. And what we notice, interestingly, is that the noise of the bilinear interpolation actually seems quite large as you get at the 90-degree points of the rotation. And I think, you know, this, when you're close to a sort of pure 90-degree rotation, you can get this weird effects. Okay, so this is what our new 360 data point data set of this 6 looks like. And then I've shown, of course, on the right, I mean, a lot of these I would argue are 9s. So there's a limit to how far we can rotate and we still believe it's 6. So the notion is that we should think of, or we could think of, high dimensional data as living on a low dimensional manifold, in this case, 1-dimensional, in a very, very high dimensional space. So let me just pause because I realize I've not brought the chat thing up, so I won't necessarily see if you're asking questions. Make sure that up. Do feel free to sort of ask questions as we're going. I've got the chat right in front of me now, so if you ask anything, you want to interrupt, you should feel free to do so. So the notion here is that this curve is 1-dimensional, right? But it's living in a 3,648 dimensional space. And the relationship between this 1-dimensional curve, I mean, there's some noise as well, so it's a little bit higher than 1-dimensional, yeah. And the 3,648 dimensional space is some kind of nonlinear mapping. And that's the motivation for dimensionality reduction. So of course, you should say, well, this is silly, pure rotation is too simple. I mean, a digit will remain a digit if it undergoes distortions that are not rotation. So you could have distortions such as thinning, which is where the digit's thickness reduces. You could have distortions such as translation. You could have distortions such as scale invariance. All of these distortions leave the digit being a digit. But what I would argue is for this very high dimensional data, if the structure in the data, I mean, sure, we already said cursor dimensionality, if every feature is independent, then basically there's no structure. I would argue that is by definition noise. So when you hear these arguments about cursive dimensionality, remember that basically I feel you're being told about noise. If features are independent and data points are independent, that's fine. This question here, why is it PCT number 2 and number 3? And is another first component not shown? Oh, that's a good point, actually. I think, really good question, George. I think that there's an error. I think this was an old, I had to dig this out because I did this all in MATLAB. And thanks for highlighting that. If you do it properly, it's PC1 and PC2. And I think what I probably did here accidentally was forget to remove the mean or something like that. And then that gives you potentially an additional component. I'm not sure, George. Good question. I do remember, for some reason, thinking for a while that the dominant principal component didn't show this variance. And then I redid it another time, and it is PC1 and PC2. It should be. If you do it correctly, it's PC1 and PC2. What happened here, I was trying to redo it in Python for you so you could recreate it, and I didn't get it done in time. And so I just dug out some old images, and I happened to have dug out the ones where I did it wrong from a long time ago. Sorry about that, George. Great question. Shows you're following. So yeah, we expect for high dimensional data with structure, maybe we don't expect to be one-dimensional implicit, but what I would argue is I almost define structure as there's going to be fewer distortions on the data than there are dimensions of the data. And so my sort of conclusion here, and this is something, this has fascinated me for a long time, is that we should be dealing with high dimensional data through dimensionality reduction. Okay, so if we're going to model it in an unsupervised way, remember we're talking about unsupervised learning here, then a really interesting approach is to take the high dimensional data and try and discover what these low dimensional distortions are and model those rather than trying to model directly in the high dimensional space. Sometimes people talk about this as being the intrinsic dimensionality of the data rather than the actual dimensionality. And if you are familiar with physical systems, you can sort of almost think about it as the degrees of freedom in the data. But of course, we don't know that there's a physical process behind these data. So we don't know what the correct number of degrees of freedom is. And that's one of the challenges we face. So I sometimes like to think of this because a lot of the work I did on dimensionality reduction did with motion capture data, which is really nice because it's high dimensional data. If you look at a stick figure that humans have a really good understanding of. And it was actually Michael Black, who's at Max Planck Institute in Tübingen, did a talk at Europe's once showing all these videos of stick data, which you could see people looking very realistic motions that you can identify, even though it's very high dimensional data. So a high dimensional data set that humans are really good at identifying whether it's good quality or not is human motion. So sometimes I like to sort of give this analogy of what you're trying to do, which is that you've got, it's what I call the marionette analogy. So like the puppeteer, it holds the marionette and moves it in a low dimensional space. Now below, the marionette is a high dimensional object. It's got arms and legs and everything's moving. But the fundamental driving dimensionality of the system is low dimensional. And that's the notion of dimensionality reduction that we're going to be exploring for unsupervised learning with Gaussian processes. So yeah, that's just saying the same thing that I guess was hopefully obvious from the analogy. Now, these techniques go back a long, long way. So a really interesting fact about them is that they actually come more out of the social sciences than maths or statistics. So if you go all the way back to about 120 years ago, people in the social sciences were looking to try and explain data sets they had through a reduced number of factors. I mean, and some of these are obviously quite controversial, such as IQ. But if you are ever doing one of these, if you've ever been asked to do one of these tests, I mean, actually, I've got stuff. When I was at Amazon, they were in the habit of constantly making us do personality tests. And like I have these things that show my personality according to these personality tests. That they've got little, they're all about how you work together in teams. So they're like Myers-Briggs, but companies do them. And they're supposed to sort of show the different personalities. I think actually they're quite effective in helping a team understand the individuals and how they work together. But they're very low dimensional in terms of how they're assessing human beings. I mean, this one has, there's basically, you have 4 colors. So it says all human beings in effect are 4-dimensional. I think it also had some additional aspect about whether you're an extrovert or an introvert. And this one seems to have the same 4 colors, and the colors seem to map up, and they all have different explanations about why these colors are the right ways of thinking about it. But it's just basically a way of taking personalities, very, very complex people, and projecting them down into a low-dimensional space. I'm fascinated by our obsession with political belief being left-wing or right-wing, like as if you can sum up all the different ways people must think about doing stuff in the world, and then it's just one-dimensional in the end. I mean, that just can't be right. I mean, it must be a function of our political systems that we end up with these sort of 2 opposites somehow going on. And I guess what is considered left-wing and right-wing over time has changed. But then we also see that these techniques, so those ideas go like way, way back. They're 120 years old. And that's the origin of an approach we're going to talk about called factor analysis. But if you go today, you also see very similar approaches being used in very modern machine learning systems. Like machine learning translation is now, as far as I understand, mostly done by seek-to-seek models that project the words into a continuous space. And another example of that is word-to-vec, where it's a sort of dimensionality. Well, it's interesting, it's conceptually, it's moving from discrete space of words to continuous space of word vectors. So words are taken and projected into some space, which isn't that low dimensional. I don't know exactly what the vector space is for word-to-vec. If anyone knows, pop it in the chat. So some dimensionality where the word lives in this vector space instead of this discrete space, and then you do your machine learning on the Daniel's saying it's up to the user. Yeah, I think you're right, it would be up to the user, Daniel, but I think that doesn't word-to-vec have oh, thanks Seb, 50 to 300, yeah. But I thought word-to-vec itself, there's some standard version you can use which had some dimensionality, but 50 to 300 sounds about right, Seb. Yeah, typically a few hundred. Thanks, Matt. So all of these things are doing some sort of dimensionality reduction, but they're not all linear. Some are linear and some are doing nonlinear. Now, we're going to go back to nonlinear dimensionality reduction shortly. And I should say my obsession with nonlinear dimensionality reduction goes back to when I was a PhD student, and talks by David Mackay in the Cavendish lab on density networks, and works by my supervisor, Chris Bishop, on something called the generative topographic mapping. But we're going to do nonlinear dimensionality reduction for the second half. But before that, we're going to look at linear dimensionality reduction. And before that, I want to review some Gaussian density properties, because Gaussians keep appearing in these cases, and it's basically due to the next 4 slides. I mean, in some sense, we could stop after the next 4 slides because everything you need to know is there. That's the beauty of Gaussians. So just to review, when we're dealing with Gaussian probabilities, a sum of Gaussian variables is also Gaussian. Now, I always try and emphasize how odd this is, because when you're told it for the first time, and now you're all used to it, perhaps, it doesn't seem odd, because you think, oh, well, that's nice. You know, 2 things add and they're Gaussian at the beginning, and then they add and they're still Gaussian. Well, it doesn't necessarily feel like that should be unusual. But of course, if you've spent some time with probability, you'll know that is unusual. That most, if you sample from most probability densities or distributions, and you add the 2 samples together, you don't stay within the same class of probability distributions. You go to a different class, and very often you can't even analytically write down what the class you've moved to is. You have to look at the characteristic function, which is like the Fourier transform of the probability distribution. And you have to map into that Fourier transform, work out what the new one is, and then map back. And sometimes you can't do the reverse Fourier transform. And so the thing doesn't actually exist. What's remarkable about the Gaussian is not only do adding two Gaussian random variables lead to a new Gaussian, and the new Gaussian has these properties of the mean of the new Gaussian is the sum of the means of the original, and the variance is the sum of the variances. Yeah, so that's kind of clean as well. So not only do Gaussian variables do this, but for any distribution, as long as it's finite variance, if you sum any distribution together, they tend towards Gaussian. And that's, as you likely know, known as the central limit theorem, right? So it's one reason Gaussian pops up so much, because if there's additive processes behind what you're seeing, then things will tend to start looking Gaussian. In fact, one approach to finding interesting things in high dimensions is to seek non-Gaussian dimensions, because you expect most uninteresting things, in some sense, are thought to occur in Gaussian directions. So this is a really important property. The next property is less special, but it's also sort of important for what we're going to do next, which is if I scale a Gaussian random variable. So if I have a Gaussian variable y sample from a Gaussian with mean mu and variance sigma squared, the scaled variable is just sampled from a scaled version of the mean and a scaled squared version of the variance. That's less peculiar. Lots of distributions stay within the same family when you scale them. In fact, many distributions have what we would call the scale parameter. In fact, we can think of sigma squared as a scale parameter in there that precisely allows this movement to occur within that class of distributions. So that's less unusual. But this maps to something quite important for us. So hopefully you'll be familiar with multivariate Gaussians because they're going to sort of pop up all across this. If you're not, there's linked material in the notes for going to do some review. But this is the sort of effect in multi-dimensions. So matrix multiplication, which is what I'm meaning to indicate at the top here, is simply scaling and adding variables together. So obviously, when I multiply this matrix W by this vector X, I'm going to get a vector Y. Now, and then I'm adding here some Gaussian variable to it. So X here, what I'm saying is X is drawn from a Gaussian density, a multivariate Gaussian. So it's got a mean mu, and that's a vector, which is the same dimensionality of X, and a covariance C. The covariance is a matrix, which is a square matrix, and it's the dimensionality of, so if X is n dimensional, then C is n by n, right? So I'm sampling this from multivariate Gaussian, and then I'm going to add zero mean. I could make this non-zero, but I'm adding zero mean Gaussian noise to it. Now, if this is all true, then the following is true: that Y is sampled from a multivariate Gaussian with a mean which is given by the matrix multiplication of W and mu, and a covariance which is given by W, this is called a quadratic form sometimes, W, C, W transpose. It's a quadratic form because W is appearing twice, right? If it was scalar, it would look just like the previous. Ignore the sigma for the moment. It looks exactly like this in the scalar case, yeah? So there's a quadratic form here, but this WCW transpose keeps this covariance matrix symmetric. So in some sense here, to do this multivariate thing, we're doing a matrix multiplication, and the matrix multiplication is leading to exactly the same thing we saw on the scaling, although hidden inside that matrix multiplication, of course, we're summing variables. So this works with Gaussians. It does not work with general multivariate distributions. And then we've got this new covariance form, which is in this quadratic form. And then if we add this zero mean, if we added a non-zero mean, we'd just see a mean term being added here. But I've added a zero mean just to sort of show that if you add a zero mean Gaussian, then you sum the covariances. So those are multivariate properties, which are sort of directly analogous to the properties for the univariate, the scalar case. And in some sense, this formula here is just at the heart of everything that's going to follow, because this is the formula behind factor analysis, probabilistic PCA, a bunch of different probabilistic approaches. But we're going to sort of go through that a little bit slower. Questions at that point about anything there? To do this thing, everyone's still with us yet? No questions? Okay. Sort of, I was having a straw poll of the part 2 students in Queen's to see what playback speed they use for playing back lectures, and I think no one said 1. No one said 2 either. So maybe I don't know what you're so used to playing back lectures now, having it live at speed 1. It's probably too slow. But the problem is you can't pause me. Okay, so so these factor analysis models that we talked about for representing personalities or intelligence or whatever they were being built to do, what they say is that there's some sort of latent space, Z, which is the sort of true thing, that's your yellow color on the personality or something like that. And then that's mapping to what we see in terms of the data we've asked for. Now, if you ever look at those Myers-Briggs tests or whatever, the data tends to be questions about circumstances and what you're more comfortable with. You know, are you the sort of person who likes to talk to other people at parties or not? I don't know, that's the extrovert introvert thing. You know, what type of jobs you'd like. So that would be the data in this case. But in general, in machine learning, this data could be anything, and we had the sort of pixels. So this is the way, what we're trying to sort of see is that this Z is that low dimensional space, which is sort of indicating in the digit rotation space how much rotation has occurred or how much thinning, and Y is then the image we see. So what we're saying is that we see something that is a nonlinear function of that space. But then we sort of say for factor analysis, okay, nonlinear is difficult, so we're just going to linearize. So we're going to assume, and somehow, yeah, so in the factor analysis, that this function here is just a multivariate linear function. In general, this function will always be multivariate. So in general, each data, what we can think of is that there's different dimensions to this F. Okay, so it's p dimensional. I'm using p. Machine learners tend to like to use d. Statisticians like to use p for data dimensionality. So p is the high dimensional output, 3,648 in the digit case. Z is some low dimensional space, which often we think of as q dimensional. I like that because then you see you're minding your p's and q's. So Z is this low dimensional thing. If the jokes are bad, you can type groan into the chat. You've got this p dimensional vector, which is a function of a q dimensional space. Now, the way we've written it here, this matrix multiplication, we could rewrite that each element here of this vector of outputs is just an inner product between one row of that matrix and the latent position. And in this case, we're going to assume that the noise, so this is the noise that corrupts, just like we had that little bit of fluctuation away from the sort of line, the circle, when we were close to the 90-degree rotation. Yeah, so here we're assuming that's Gaussian. So what we see is some linear projection of the space plus some Gaussian noise. So we're assuming that's Gaussian. Now here, notice here, I've indexed the variance of that noise with J. So that implies that I'm expecting the variance of that noise to be different in each dimension of Y. And that's important because that's a factor analysis assumption. That's actually the key assumption behind factor analysis, that noise varies. And as we vary that assumption, we get different methods. So what I want you to think of is we're going to map this into a matrix form now, because so I always like to use design matrices because they come from statistics, right? And, you know, statisticians defined this before machine learners were on the scene. So it's a bit annoying if we just redefine it, but it's a convention. So my data here is Y. In the digits case, it's going to be the flattened image is Y1 is the, you know, the 6, but flattened from an image to a sort of a vector. And then each rotated image is going to be Y2, Y3, but they're sitting in the rows of Y. So Y has n rows and p columns. And that's the convention of the design matrix, that you put the data points along the rows. Now, I guess people, because they think of data points as vectors, and vectors are by default columns, sometimes put it the other way. But I prefer this convention because it's standard across stats. It's just the same as choosing to drive on the left or right. Yeah, it doesn't really matter. I mean, there's no wrong reason to do one or the other. I mean, apart from people are left-handed or right-handed and want to change gears, but you know, that's in the details. There's no real reason to do one or the other, but it is important that people keep the same convention. So since the statisticians got there first, we put the rows, the data points on the rows, just like driving on the left came before driving on the right. And so then we can write down, so F here is the sort of pre-corrupted manifold. And if we want to write down the whole matrix of Fs, this is the little thing about when you're doing it this way, the matrix form becomes ZW transpose. So the reason for that is because this Z is a column vector, right? And if we're going to turn it into a design matrix form, so the Z design matrix has number of data points along the rows and Q columns, then in order for all the dimensionalities to match up, this is the form that we write down this linear system in. So I just wanted to highlight that. Okay, so little exercise, persuade yourself of that. Not going to take you any time. It's in the, but if you're familiar with linear algebra, you know, all I mean for you to do here is map out these linear algebra things and show yourself that these things are true. Just as a way of getting familiar with some of these matrix operations, because having that familiarity for reading some of the papers you're going to look at is kind of important. Now, want to highlight this because there's this sort of really interesting sort of duality between latent variable models and linear regression, or I should say Bayesian linear regression, so probabilistic linear regression. So in the latent variable model, so I don't know why I've got that X there. Ignore that for the moment. I may realize why it's there in a moment, but ignore it for the moment. I think that this shouldn't be here. I think that's coming from the notes. If Z, so latent variables are unobserved. So we don't know what the rotation was. We don't, before we, you know, we don't know what the, if this is the sort of fundamental thing that's defining what this object is, when we look at the digit, we don't know how it's rotated away from the prototype. We don't even know what the prototype necessarily looked like. Or we don't know the sort of fundamental how left wing or right wing this individual is. So when we first look at something, it's a parameter we don't know. And a really nice way of dealing with parameters we don't know is with probability distributions. And that's what latent variable models do. So what we're going to do here is assume that these factors, these latent factors, are drawn from a Gaussian distribution. So in this case, they're drawn from a Gaussian with mean 0 and covariance, which is the identity matrix. So that's like a circular whitened Gaussian with variance 1 in each direction. Now, when we look at what F is, if that is Z, we can use our multivariate rules to immediately see that, okay, the mean was 0, so the new mean is W times the mean, which is 0. The covariance is W times the original covariance times W transpose. Well, that's what we've got here, W transpose. and we're not adding anything to this yet. So this is the covariance of F. So what we're doing here, and you'll, by the way, see this in variational autoencoders, and everyone's doing it now. I mean, these methods are quite common now, but there used to be a time when people weren't doing this very much. You're sort of putting a Gaussian distribution in a latent space, and here in a variational autoencoder, you would use a neural network, right? So actually everything we've said so far, if we were to replace this thing with a neural network here, then this would be like, well, variational autoencoder implies a particular algorithm to fitting it, but this would give us the probabilistic model behind a variational autoencoder. And that's what density networks were. So David Mackay was doing that back in 1995, I think, called it density networks. It was a different inference algorithm. Inference here, I mean, not prediction. I mean, trying to do the probabilistic inference, infer the posterior distributions. Okay, so now if we add in the noise, so if we add in the noise, that's what that was probably. I think this is supposed to be about the noise. If we add in the noise, then that just means adding in the variance of the noise, which we said was independent and had a different variance for each dimension. So this gives us this distribution for the data, right? So this assumption that the data we're seeing is drawn from a low dimensional space and then mapped up to higher dimensions in a linear way and then corrupted by noise is equivalent to this model for a single data point. I'm going to pause there, see if there are any questions. How are we doing time-wise? In fact, we can pause there for questions and break. Yeah. So let me just stop sharing for a while. And I'm going to stop recording in case there's questions you want to ask off the recording.